Distribution of elementary particles and quantum numbers.
Hi, my name is Mohammad Hilmi, and I'm going to talk about elementary particles and quantum number. What is elementary particle? Elementary particle can be either bosons or fermions. Boson is a particle that follows Bose-Einstein statistics, while fermion is a particle that follows Fermi-Dirac statistics. Boson made up one of two classes of elementary particles, but fermion has half-odd integer spins like 1/2, 3/2, and others. Fermions include all quarks and leptons, as well as all composite particles made of an odd number of these, such as all baryons and many atoms and nuclei. These particles obey the Pauli exclusion principle. So, what is quantum number? Quantum number is the values of conserved quantities in the dynamics of a quantum system. The energy levels of electrons in an atom are often described specifically by quantum numbers. Other possibilities include angular momentum, spin, and more. A specification of all of the quantum numbers of a quantum system fully characterizes a basic state of the system and can be measured together. Four quantum numbers can describe an electron in an atom completely. The first one is principal quantum number, which is n. The second one is azimuthal quantum number, which is L. The third is magnetic quantum number, which is mL. The last one is spin quantum number, which is S.
History of elementary particles.
Hello everyone, I'm Lina. So today I'm going to talk about the history of elementary particle and baryon and lepton numbers. First, J.J. Thomson discovered the subatomic particles electron in 1987. Then, Amos Rutherford discovered the nucleus of the atom in 1911. But then, in 1928, T.A.M. Dirac hypothesized that the existence of a positively charged electron, which is called a positron. It was detected in 1932. Other than that, in 1932, neutron was discovered by James Chadwick, and the atom was seen to consist of protons and neutrons in the nucleus and surrounded by orbiting electrons. Next, in 1934, the existence of the neutrino was established in theory. In 1925, Hideki Yukawa suggested that meson may be exchanged between nucleons. Meson is a charged particle with a mass intermediate between those of the electron and proton. Then, in 1947, meson was discovered and named the pi meson. Then neutrino was detected in 1956 after established the theory in 1934. Then in the 1950s, the production of a particle collision in the particle accelerator gives the result of the observation of these elementary particles.
Baryon numbers and lepton numbers.
Let's go to baryon and lepton numbers. The baryon and the three families of the leptons are characterized by one set of quantum numbers. The baryon and lepton are strictly conservative additive quantum numbers of a system. Firstly, the baryon number, positive 1, is assigned to all baryons, which are 3 quarks. Mesons consist of 1 quark and 1 antiquarks is B0. And if it's negative 1, to all antibaryons or 3 antiquarks. If B equals to 0, it's the result of quark of one color with an antiquark of the anticolor. Example, leptons, vector bosons, Higgs boson, graviton are the particles without any quarks and baryon number is 0. While B is equal to 1 is the result of 3 quarks of different colors. When it is negative 1, it's the result of 3 antiquarks or different anticolors. Before the establishment of the quark model, the baryon number was defined. Therefore, particle physicists give baryon number is the 1/3 of the quarks, rather than changing the definitions. It would be more accurate to speak the conservative of quark numbers nowadays. Next, for lepton numbers was introduced in 1953. The process of inverse beta decay conserves lepton numbers as the incoming antineutrino has the lepton number of 1, while the outgoing positron also has lepton number of -1. For Le, the electron number for the electron and the electron neutrino. Le equal to 1 is assigned to the electron and the E neutrino, while Le equals to -1 to their antiparticles, or all the other particles have Le equals to 0. Next, we are going to look at the muon number and the tau number. For the muon number is for the muon and the muon neutrino is only equals to 1, while the tau number for the tau and the tau neutrino is equal to 1 as well.
Neutron decay.
The decay of free neutrons is energy feasible because the mass of a neutron is greater than the sum of the masses of the proton and electron it decays into. But where a neutron is paired with a proton, its decay is not energy feasible, and thus such neutrons within nuclei are stable. Decaying is the only way neutron can conserve both energy and baryon numbers. B. The two decays are pion and muon, while the other one is pair production. These decays can conserve the lepton numbers during the process.
Strangeness.
Strange particles is defined as a number of particles that behave unexpectedly. These particles only created in pairs and decay only in certain ways. Strangeness number can be defined by a letter S. S is conserved in all processes mediated by electromagnetic interactions. In the other hand, S also can change in an event mediated by the weak interaction. These processes are relatively slow, a billion or more times slower than decays that proceed via the strong interaction. Even the weak interaction doesn't allow S to change by more than or less than 1 in a decay.
Symmetry and conservation of principles.
Why is the relationship between conservation laws and symmetries important? One reason is that it allows for other conservation laws to be formulated. For example, for conduction electrons in solids, all locations in the solid are not equivalent. For one, some locations are closer to nuclei than others. Therefore, linear momentum of the electrons is not conserved. Every conservation principle corresponds to a symmetry in nature. How are the conservation laws related to the symmetries of the nature? It states that the amount of the conserved quantity at a point or within a volume can only change by the amount of the quantity which flows in or out of the volume. From Noether's theorem, each conservation law is associated with a symmetry in the underlying physics, which is a differentiable symmetry of nature. The simplest symmetry operation is translation in space, which means that the laws of physics don't depend on where we choose the origin of our coordinate system to be. A German mathematician, Emil Noether, showed that the invariance of the description of nature to translations in space has, as a consequence, conservation of linear momentum. Another simple symmetry operation is translation in time, which means that the laws of physics don't depend on when we choose t equals to 0 to be, and this invariance has as a sequence conservation of energy. Invariance and the rotations in space, which means that the laws of physics don't depend on the orientation of the coordinate system, in which they are expressed as a consequence the conservation of angular momentum.
The Eightfold Way.
A classification for hadrons, called the Eightfold Way, may encompass the many short-lived resonance particles as well as the relatively stable hadrons. Many attempts have been made in trying to discover a system of organization that group elementary particles into larger groups of identification. The only one that has had much success is the Eightfold Way, proposed independently in 1961 by both Murray-Gell-Mann and Yuval Neeman. The Eightfold Way groups the baryon and mesons into geometrical patterns of the same baryon number, spin, and parity. An example of one of these shapes is the baryon octet, which consists of the 8 lightest baryons. Notice how the particles are arranged in a hexagonal form with 2 baryons in the center. Each of these baryons has a baryon number of 1, a spin of 1/2, and positive parity. Also note that in the Eightfold Way, strangeness S is plotted horizontally and the quantum number I3 is plotted vertically. The symmetry of charge Q along the diagonal of the figure develops just by plotting strangeness versus quantum number. Not only does a neat geometric shape appear, a change charge automatically develops into a perfect symmetry as well.